Hi guys, it's Mrs. Allison. Today we are going to look at direction fields and the existence and uniqueness of solutions and how this all plays into our differential equations. So, you guys, direction fields you've done before. Another name for direction fields is slope fields. This is what we've done since last year in calculus. So we learned how to sketch slope fields last year. What we know about slope fields is that at each point, each ordered pair, the little arrow that we draw represents the slope at that point. Now, with differential equations, we actually draw them with arrows, with direction a lot of times. So you may see them with arrows. You can see them without as well, but typically with arrows. Now, there's two purposes for these direction fields, or there's two nice pieces of information that we can get. And the first one is a sketch of the solutions. So each of these arrows in the direction field are tangents to the actual solution, the actual solutions of the differential equation. So we can use these tangents as a guide to sketch the graph of the solution to the differential equations. Also, we know that the long-term behavior, oftentimes we don't actually want to know a specific solution. We want to be able to make predictions as to what's going to happen as certain variables change, or as time goes on, or as our x increases. And so these direction fields can be used to find information about this long-term behavior of the solution. What happens as we go further out? So let's look at an example of a direction field and what it might look like. So let's say we were given a direction field. Okay, I really don't know what equation this came from, but if we were given a direction field like the one here at the right, what we would want to do is we would want to know what the solutions look like. So let's sketch a solution where the initial value is 30. Well, what that means is we're going to start here at 30, and each of these arrows represents a tangent that the line or the solution has to be tangent to. So each of these little segments is tangent to my actual solution. So if I were to draw a solution curve in here, I might draw something that's tangent right here, and we'll pretend that's straight. Goodness. It's not straight, but it should be curved slightly. So let's draw that. So my curve, I don't know why these don't draw straight with this iPad pen. My curve might look something like this. So you can see that at the points that I was trying to get at, this tangent here that we had, this direction here is tangent to that curve. And this one is tangent to that curve. And you can see that each of those, theoretically, were tangent to what we believe the solution curve is. Now, as we look through this, we might be able to sketch a few more solution curves. I see one in my mind that stands out pretty readily, and that's this 50. And if I were to sketch the solution curve right here with the initial value of 50, I might have a horizontal line. Whereas if I sketch a solution curve at 80, I might have a curve that looks something like this. I kind of had a weird jog at the end. But I might have a curve that looks something like that. So you can see these solution curves as we go through. These curves will help us make predictions long term about what is happening with this particular differential equation. Now, the set of solutions that we've graphed are called the family of solution curves. Because that's not any different than it was in calculus. Now, we may also call these the set of integral curves, and we didn't call it that in calculus, but same idea. Okay, so let's talk about some of these different pieces that you're going to see. We have several different definitions that I want to define today, and then we're going to look at what they look like. So an equilibrium solution is a solution to a differential equation whose derivative is zero. Oops, I need the S. Is zero. So an equilibrium solution is a solution to the differential equation whose derivative is zero everywhere. So if we picture this on a graph, the equilibrium solution is going to be a horizontal line. Well, we saw an equilibrium solution up here, and that was when my initial value was 50. So given a slope field, we can find the equilibrium solutions by looking for where the horizontal lines are. Now, equilibrium solutions actually have two different types. The first type, well, three different types really, and these are best understood when we look at a slope field. But we have a stable equilibrium solution. And a stable equilibrium solution is one where other solutions are trying to get to this. So a stable equilibrium solution is one where the other solutions are trying to get to it. So if we pick a point a little bit off that equilibrium in either direction, right, and we were to draw our curve is going to tend towards that equilibrium solution. So you can see this 50 would be what we call a stable equilibrium solution because these curves are trying to get to it. The other curves are trying to get to it. Now, an unstable equilibrium solution is one where the other solutions are trying to get away from it. I don't actually have an unstable equilibrium solution in the example up above, but an unstable equilibrium solution is one where the other solutions are trying to move away. We'll look at an example in just a minute. Now, in cases where solutions on one side of the equilibrium move towards, but the other side they move away from, we call that equilibrium solution semi-stable. So this is where one side solution tends towards, solutions tend towards, and one side solutions tend away. That would be a semi-stable equilibrium solution. Okay, let's look at an example. This next example says we want to sketch the direction field for the following differential equation. So we have the equation dy over dt equals y squared minus 4 times y plus 1 squared. What I'm going to do is I am going to first figure out where my derivatives are equal to 0. So the equilibrium solutions occur when the derivative is 0. That's what the definition is. So what I'm going to do is I'm going to let y prime be 0. I'm going to let my derivative be 0. And I'm trying to figure out when 0 equals y squared minus 4 and when 0 equals y plus 1 squared. So on this first one, I would get an equilibrium solution at plus or minus 2. And over here, I would get an equilibrium solution at negative 1. So we can represent these equilibrium solutions here at positive 2. I'm just going to draw horizontal lines. I have negative 2. I don't know why that one got so big, but that's okay. And then I have negative 1 as an equilibrium solution as well. Okay, so these are my equilibrium solutions. We may even want to notate these with horizontal lines through them. Now, if I were to look at my direction field for this, what I would do is I would take points, if I can, and substitute them in to figure out what this should be. I just noticed that this, well, I didn't label the axes. I guess we can call that T. In my head it was X, but it says T. So anyway, this would be my T axis, and this would be my Y axis. Okay. So if I look at these, I may plug in points. So for example, if I let Y be 3, and I plug 3 in, I'd get 5, and then 3 plus 1 is 4 squared is 16. So I'd have a pretty positive number, like drastically positive number if I'm plugging in 3. So my direction fields are going to be really steep. Well, I don't know what they look like, and it didn't really matter what the X was, but that slope when Y is 3 is really, really steep. And if I let Y be 1, and I substitute that into my equation, I'd have 1 squared minus 4, so negative 3, times 2 squared. Sorry, 2 squared. So negative 3 times 2. So I get a negative 12. So it's still pretty steep, but I'm in the negative direction. So whatever's happening at negative 1, I'm pretty steep, but not quite as steep as whatever that last one was, 45. Okay, so if we visualize this, these curves are going to have to be tangent to this. So something's happening up here and down here where this curve is moving away from, right? We're moving away from this equilibrium solution. So this equilibrium solution, since we're moving away from it, the equilibrium solution of Y equals positive 2 would be unstable. Okay, let's keep going because my curves are getting ugly. But let's see what happens like if we plugged in 0.5 for my Y. If I plug in, negative 0.5 even. Let's do negative 0.5. If we substitute in negative 0.5, negative 0.5 plus 1 squared is going to be positive. Negative 0.5 squared will be positive minus 4 is going to be a negative number. So this is going to be negative, but a pretty shallow negative, meaning not very negative. And so this is going to be, right? So we're going to have negative. And so if we follow these curves, we might have something that looks like this as we follow those curves towards it. And so let's see what happens in between negative 2 and negative 1. So if we plug in something like negative 1.5, negative 1.5 squared minus 4 is still a negative number. And negative 1.5 plus 1 would be a negative number squared. It's not going to be a very negative number, but it's still going to be tending towards the negative. So we might draw these direction lines again this way. And then let's plug in something like negative 3. If we plug in negative 3 up here, we would have 9 minus 4, and we're back to where we started, where we have that really steep, positive direction field. And what we can see here is then that's going to mean these graphs are going to curve towards this. And this is curving towards this. Okay, so we're going to call when Y equals negative 2 stable because all of the solution curves are coming towards it from both directions. And then we're going to call Y equals negative 1 semi-stable because one side is tending towards it and one side is tending away. So my equilibrium solutions are Y equals 2, Y equals negative 2, and Y equals negative 1. And some are stable, some are unstable. Now, when we get into higher dimensions of differential equations, we might call the solutions that are nearby this stable equilibrium, which was -2, we might call these a sink. And if you picture it in 3 space, if everything's tending towards a point, you might visualize it all going down like almost like a drain, like everything's going down a drain. And what we call solutions, or the equilibrium solution here, would be a source where everything's coming from that solution. Okay, so you may hear those phrases as well, sink and source. The reason for them, you can kind of see on those graphs. So hit pause and let's try this next example. It says, find all the equilibrium solutions of y prime equals y cubed minus 2y squared and determine the stability of each one. So hit pause and try it. All right, so the first thing I'm going to do is I'm going to factor this. So we get y prime equals y squared times y minus 2. And setting each of those equal to 0, I get y equals 0 is an equilibrium solution and y equals 2 is an equilibrium solution. So let's look at both of those, and I will draw those in red. I'm just going to draw dotted lines. So these are my equilibrium solutions. Now what I really need to do is just figure out which direction the slopes are moving. I didn't ask for a direction. I didn't ask for a slope field derivative, or oh my goodness, slope field generator or direction field. I didn't ask for that. All I really need to know is what is happening. So I don't really need to know what the solution curves are going to potentially look like. All I know is I need to figure out the slope at each of these intervals. So something above 2, if I plug 2 into here, I would get positive and positive. Therefore, this slope here will be a positive number. Right? So the slopes will be going up. And if I plug in, say, 1 will be positive for y squared, but negative for y minus 2. So this will be negative. And so I can see right away that y equals 2 is an unstable equilibrium solution because things are moving away from it. And now let's look at y equals 0. And if we look at y equals 0 and substitute in something lower, like -1, we'd have positive times a negative, so it is also a negative. And therefore, y equals 0 is a semi-stable. You may also see this called the source because everything is originating from this equilibrium solution. Okay, now sometimes the right side of the differential equation, because typically we put that differential on the left side, the right side of a differential equation contains both the function and an independent variable, and we haven't seen that so far. All we've looked at is our function, y. And so the behavior can be a little bit more complicated when we're dealing with a differential equation that has both the function and the independent variable. You guys, their computer softwares are going to be your friend in this case. Desmos has a fantastic slope field generator. So if you just Google Desmos slope field generator, you can type in your equation and it will generate what the slope field looks like for you. So you don't have to figure it out. But I want to show you how sometimes it's not so hard. And then we'll look at what the Desmos one looks like. When we're doing a direction field for something like y prime equals y minus x. When we want to do this, we want to identify the places where the derivatives will be constant, meaning the same. So the easiest way to go about this is to deal with, say, start with a slope like m equals 0. Is there a place along here where m equals 0? Well, is there ever a place where 0 equals y minus x? And yes, there's a place where y equals x. So if I look at 0, I would have slopes, any place where y equals x, I would have slopes of 0. Well, I can look at another one. Let's do m equals 1. When m equals 1, I have 1 equals y minus x, which means that I get y equals x plus 1. And if we look at the slope of 1, when y equals x plus 1 would be a line that would go through these points. Well, the slope is going to be 1, so I'm going to have a slope of 1 like this. And we could continue on building our different constant places where the derivative would be constant, and we could keep going. Each of these are called isoclines. Okay? Each of these places along here, and notice I did them in different colors. Desmos did it a little bit different. But these are called isoclines. Okay? An isocline we can plot on each of these curves, and the derivative will be a constant value. Okay, so here's what Desmos looks like. They graphed it, and I obviously graphed a significant number more points here. I went from -10 to 10 on both the x and the y, but you can see these isoclines as we go through. You can see that y equals x plus 1. You can see where y equals 0 along here, and as we keep going, you would see the different patterns along based on their slopes. Okay, so sometimes it can be done by hand. Sometimes we can use a graphing calculator like Desmos to do a slope field generator. Now, we need to continue this discussion to talk about existence and uniqueness. Existence and uniqueness. Okay, so the graphical analysis of a differential equation suggests that we can always find a solution to a curve passing through any point. Is this true? Well, maybe. But if we find a solution, there's several things we want to know. First of all, when does a solution to an initial value problem actually exist? And if it does exist, is it unique? Why is this important? Well, it'd be really silly to study these differential equations or to work through a whole differential equation only to find out a solution doesn't actually exist. And it would also be kind of silly to try to use a solution to make a prediction about what is happening if we don't know the solution's unique. Because if the solution's not unique, then making a prediction using that solution is not helpful. We wouldn't know which solution we were talking about. Well, there's a theorem that says if f is continuous near AB, let me back up. Given we have a differential equation that looks like this, dy over dx equals some function with respect to x and y, and we have an initial condition y of a equals b. Then, if f is continuous near AB, the point AB, then a solution exists. Okay? What the heck do we mean by saying it is near, it's continuous near? Well, let's say I have some solution. Let's just graph, and let's graph a curve. So some curve, and I have a point AB. So we'll call this A, and then we'll call this B. So I have this point, AB, and this is my solution. Okay, so my solution is this curve, this function. If I'm going to be a solution that is near AB to determine if it exists, it means I'm going to be in the vicinity, whatever that vicinity looks like. Maybe it's here. I'm going to be near AB. So this is what it means to be near AB. Now, the tricky part about this near AB is it's really just an infinitesimally small amount away from AB. You get outside AB very much, and this solution may not exist at all. But if f is continuous near AB, then the solution exists. But if also the partial derivative with respect to y is continuous near AB, then we can say the solution will be unique. Okay? It's only near AB, but we don't really know how far around it exists or is unique. So it's not a guarantee that it works everywhere. It is just looking at that particular point at that particular moment, that AB. But we can determine existence and uniqueness. So let's look at an example. Let's consider the initial value problem that says y prime equals y to the 2/3 power. And it gives us the initial value of y of 0 equals 0. I want to know, can we guarantee that a solution exists? And then why or why not? Well, the first thing we would need to determine if dy dx, if it's dy dx, I guess it doesn't have to be, if y prime is continuous over a region around that initial value. So what I'm looking for is the derivative y prime equals y to the 2/3 continuous around or near 0, 0. Is this the case? If we picture this function, is it going to be continuous? And the answer to this is yes. What we can tell from this then is we know a solution exists at 0, 0. This solution that we have or that we can find exists at 0, 0. Okay, but can we guarantee this solution is unique? Well, if we're going to guarantee if it's unique, what we need to do is we need to check the partial derivative of f with respect to y. And if we check the partial derivative of f with respect to y, we get, let's see, 2/3. So if I take the partial derivative with respect to y, I would have 2/3 y to the negative 1/3 power. And therefore, this would be 2 over 3 cube root of y. So if it's going to be unique, then I want to know, is the partial derivative with respect to y, which is 2 over 3 cube root of y, continuous around 0, 0. If it's continuous around 0, 0, then it's unique. But here's the problem. That's not continuous around 0, 0. Therefore, this is not going to be a unique solution. Now, why is this helpful? Well, I know I can solve it. The solution exists. But what I know is I can't base every prediction on that solution because it's not the only one. There may be more, or there are more. So that is guaranteeing or looking at existence and uniqueness. Now we'll start to look at how to solve these. The separable differential equations, we'll start talking about them tomorrow. So have a great day, and we will see you soon.